Let's kick things off by clarifying a core concept: the AI agent. Unlike a standard LLM prompt which simply takes your input and returns an output in a single linear pass, an AI agent is much more dynamic. It operates in a loop incorporating planning, memory, and tool usage. This means the agent can evaluate its own outputs, decide if it needs more information, execute external tools, and iterate until it achieves its goal. This iterative process is what sets AI agents apart from basic prompt response models, making them far more powerful for complex tasks. Next, let's explore the RAACT framework, which stands for Reason Act. This approach combines two key elements: reasoning and acting. The agent first generates a thought to analyze the current state, then takes an action like performing a web search or making an API call. Afterward, it receives an observation, which is the result of that action. This loop continues, with the agent alternating between thinking and acting until it reaches a final answer. This framework is especially useful for tasks that require both logical analysis and real-world actions. Tool calling, sometimes called function calling, is a powerful feature in modern LLMs. It allows the model to interact with external systems by outputting structured JSON objects instead of plain text. You provide the LLM with a schema describing available functions, including their names, descriptions, and arguments. When a user prompt comes in, the LLM can choose to call a function by generating the appropriate JSON. This enables seamless integration with APIs, databases, and other tools, making the agent much more capable. But what happens when things go wrong? Sometimes an LLM might hallucinate an argument or format invalid JSON during tool calling. To handle this, you can use Pydantic validation to parse the output. If there's a parsing error, you can append the error message back to the conversation history and prompt the model to correct itself, a self-correction loop. Specialized libraries like Instructor or LangChain utilities also help enforce strict schema constraints, reducing the risk of errors. In planning with agents, it's important to understand different prompting strategies: zero-shot, few-shot, and chain of thought COTI. Zero-shot means giving the agent a goal without examples. Few-shot involves providing a few examples of input-output or tool use pairs. Chain of thought prompting explicitly tells the model to think step by step, breaking down complex problems into smaller logic tokens before answering. Each strategy has its strengths, depending on the complexity and familiarity of the task. Plan and solve prompting takes a different approach from chain of thought. Instead of dynamically figuring things out step by step, a plan and solve agent drafts an entire macro plan up front, breaking the task into multiple subtasks. These subtasks are then executed sequentially or in parallel. This method is highly efficient for structured problems, where the overall plan can be mapped out before execution begins. Memory is crucial for effective agents. Short-term memory typically refers to the chat history or context window, where relevant previous turns of the conversation are passed back to the LLM. Long-term memory, on the other hand, involves storing summaries or embeddings of past conversations in an external database. When needed, the agent can retrieve this information using semantic search, ensuring it doesn't lose track of important details over time. State management is a foundational concept in agentic frameworks like LangGraph or AutoGen. Here, a centralized mutable state graph is maintained. Each step or node, such as an LLM execution or a tool call, takes the current state as input, modifies it, and passes it to the next node. This approach prevents context loss and allows for conditional routing based on the state values, making complex workflows more reliable. Sometimes, a single agent isn't enough. Multi-agent systems divide complex tasks among multiple specialized agents, such as a writer, critic, or coder agent. This approach is ideal when tasks require distinct personas, diverse toolsets, or collaborative feedback loops. Multi-agent systems help manage complexity and improve performance, especially for tasks that would overload a single agent's context window. Multi-agent architectures can be hierarchical or peer-to-peer. In a hierarchical setup, a supervisor agent orchestrates the process, delegating subtasks to child agents and managing their outputs. In peer-to-peer systems, agents communicate directly with each other based on predefined state transitions. For example, a coder agent might pass its output straight to a code reviewer. The choice depends on the workflow's complexity and the need for centralized control. Common risk in agentic workflows is getting stuck in an infinite loop. To prevent this, you can set hard technical guardrails such as a maximum number of loop iterations or a timeout ceiling. Monitoring for state drift, like repeated thoughts, also helps stop execution if the agent isn't making progress. These safeguards ensure agents remain efficient and don't waste resources. Flexion is an advanced architecture where an agent evaluates its actions through a feedback loop. If a task fails or produces poor results, a separate evaluator agent creates a critique. This critique is stored in memory, and the worker agent retries the task, using the feedback to avoid repeating mistakes. Reflection helps agents learn from errors and improve their performance over time. Security is paramount when passing authentication tokens or sensitive keys during dynamic tool calling. Never pass raw API keys or secrets into the LLM context. Instead, the LLM should output generic function arguments, and the agent framework backend injects the necessary environmental variables or authorization headers securely before making the external call. This keeps sensitive data safe from exposure. Human-in-the-loop HITL patterns pause agent execution at critical points, such as sending emails, approving transactions, or executing sensitive code. The agent saves its state and notifies a human operator who can approve, modify, or reject the action. Once the human responds, the agent resumes its workflow. This approach ensures oversight and safety in high-stakes scenarios. Long agent loops can quickly fill up the context window with token history, including thoughts, tool outputs, and system messages. This can degrade performance or hit context limits. To manage this, agents use conversation pruning, summarizing past turns, or moving historical context to a vector database. These strategies help maintain efficiency and prevent loss of important information. There are two main ways to enable tool calling: fine-tuned weights and prompt-engineered instructions. Fine-tuned models like GPT-4o are trained to reliably emit structured JSON tags when they see tool definitions. Prompt-engineered tool use relies solely on context window rules, such as instructing the model to respond in a specific format. Fine-tuned models are more robust, while prompt-based methods are more fragile and prone to errors. Measure an agent's reasoning capability. You can benchmark it on complex logic tasks like SWE-bench for software engineering, human eval for coding, or custom domain-specific test suites. These benchmarks assess task completion rates, tool execution accuracy, and the average number of steps taken. Regular benchmarking helps ensure your agents are performing as expected and highlights areas for improvement. LangGraph offers unique advantages over standard LangChain sequential chains. While sequential chains are linear and acyclic, agents often require cyclical graphs with loops, conditionals, and self-correction. LangGraph supports these cyclic architectures natively and enforces strict state schemas across steps, making it ideal for complex agentic workflows. Routing determines which step or node an agent should execute next. This can be deterministic, like routing to a debug node if a Python script errors out, or probabilistic, where the LLM decides based on the current state. Effective routing ensures agents follow the optimal path to solve tasks, adapting dynamically to changing conditions. Lost in the middle phenomenon refers to how LLMs excel at extracting information from the beginning or end of long context windows, but often miss details buried in the middle. For agents, this means that if too much historical data is stored, important facts can be overlooked. Managing context effectively is crucial to avoid this pitfall and maintain strong reasoning. Agent planning loops are at the heart of agentic workflows. These loops allow the agent to continuously evaluate its progress, make decisions, and adjust its actions as needed. By iterating through planning, acting, and observing, agents can tackle complex problems that require multiple steps and adapt to new information along the way. Key part of agentic workflows is the ability to evaluate outputs. After each action, the agent reviews the result to determine if it has achieved its goal or if further steps are needed. This self-evaluation ensures that agents don't just follow instructions blindly but actively work toward the best possible outcome. Degrading external tools is a game changer for AI agents. By connecting to APIs, databases, or other systems, agents can access real-time information, perform calculations, or trigger external processes. This expands their capabilities far beyond simple text generation, making them valuable for a wide range of applications. Effective agents need to remember past interactions. Memory retrieval allows agents to pull relevant information from previous conversations or stored data. This helps maintain context, avoid repetition, and provide more accurate responses, especially in long-running workflows. Conditional routing enables agents to make decisions based on the current state. For example, if an error occurs, the agent can route to a troubleshooting node. If a task is completed, it can move to the next step. This flexibility is essential for handling complex, branching workflows. Feedback loops are vital for continuous improvement. By analyzing the results of each action and incorporating critiques or suggestions, agents can refine their strategies and avoid repeating mistakes. This iterative process leads to smarter, more effective agents over time. Strict schema enforcement is crucial when agents interact with external tools. By validating outputs against predefined schemas, you can catch errors early and prompt the agent to correct them. This reduces the risk of failures and ensures smooth integration with other systems. As agents accumulate more context, summarization becomes essential. By condensing past interactions into concise summaries, agents can stay within context window limits while retaining important information. This technique helps maintain performance and relevance in long-running conversations. Semantic search allows agents to retrieve relevant information from large databases using meaning rather than exact keywords. By storing conversation embeddings or summaries, agents can quickly find and use past knowledge, making them more context-aware and responsive. Implementing guardrails and monitoring is essential for safe agent operation. By setting limits on iterations, timeouts, and monitoring for repeated actions, you can prevent runaway processes and ensure agents remain efficient and reliable. In multi-agent systems, collaborative feedback is key. Agents can critique each other's work, suggest improvements, and learn from one another. This collaborative approach leads to higher quality outputs and more robust solutions. Role specialization allows agents to focus on what they do best. For example, one agent might handle writing, another critiques, and a third codes. This division of labor makes complex workflows more manageable and efficient. State graphs are visual representations of an agent's workflow. Each node represents a step and edges show how state transitions occur. This structure helps prevent context loss and enables conditional routing, making complex workflows easier to design and debug. Centralized state management ensures that all agents and tools have access to the latest information. By maintaining a single source of truth, you can avoid inconsistencies and ensure smooth coordination across the workflow. Some tasks can be executed in parallel, speeding up the workflow. Agents can handle different subtasks simultaneously, then merge their results. This approach is especially useful in plan-and-solve prompting where multiple steps can be tackled at once. Effective agents know when to delegate. In hierarchical multi-agent systems, a supervisor agent assigns subtasks to specialized agents, collects their outputs, and manages the overall process. This delegation improves efficiency and ensures each task is handled by the most qualified agent. In peer-to-peer architectures, agents communicate directly with each other. This allows for faster feedback and more flexible workflows as agents can pass outputs and requests without a central supervisor. Self-correction mechanisms help agents recover from errors. By detecting mistakes, prompting for corrections, and retrying actions, agents can improve their reliability and reduce the impact of failures. Secure backend integration is essential for protecting sensitive data. By handling authentication and authorization outside the LLM context, you ensure that secrets like API keys are never exposed, maintaining a high level of security. Approval workflows add an extra layer of safety. By requiring human approval for critical actions such as financial transactions or code execution, you reduce the risk of unintended consequences and ensure accountability. Managing tokens and secrets securely is a must. By keeping sensitive information out of the LLM context and using secure storage and injection methods, you can prevent leaks and maintain trust in your agentic systems. Context compression techniques help agents stay within token limits. By summarizing, pruning, or offloading old context to external storage, agents can maintain performance and avoid losing important information. Regular testing and validation are key to maintaining agent quality. By running agents through benchmarks and regression tests, you can catch issues early and ensure consistent performance across updates. The best agentic systems are always improving. By collecting feedback, analyzing failures, and updating strategies, you can keep your agents at the cutting edge and ready for new challenges. We've covered the foundational concepts of agentic workflows, from planning and memory to tool integration and security. By mastering these principles, you'll be well equipped to build advanced AI agents for real-world applications. Keep exploring, testing, and refining your workflows to stay ahead in the rapidly evolving field of AI engineering.